Okay, hello everyone. Welcome to our last day of content lecture. So next time I see you, we will be reviewing for exam 4, and we'll take exam 4, then we will review for the final. So this is our last little push for now. So we're going to finish out strong, we're going to finish out cardiac output, and then we'll be ready to go. I have shared with you in your Brightspace folder, I shared a file full of practice sort of stuff to work through for exam 4. I will put up a practice test as usual. I just haven't got that written yet, but if you want to get to studying, there's some stuff tying everything together in there. Now there's a worksheet on the heart, there's some Google quizzes on heart stuff, there's a PowerPoint moving stuff around that involves some of our muscle stuff as well, those last couple things about fibers that we went through. We can get started in on those, and the keys are in there as well. Okay, so last time we talked, we were talking about cardiac output. So we're talking about how blood gets out to the body, right? This is something we really care about because this is important for your tissues, getting oxygen, getting glucose to make ATP so they can do their stuff, and so we can remove our waste products. So we talked about the fact that this is going to be under the control of the autonomic nervous system, both branches, the parasympathetics and the sympathetics. And we first looked at this equation. The cardiac output is equivalent to our stroke volume, so the amount that leaves the heart, the amount of blood that leaves the heart in any given minute, times our heart rate, which is our number of beats per minute. Okay. So we were beginning to talk about the factors that affect these two properties, the heart rate and the stroke volume. So just flipping back to that equation real quick, we care about this, right? Because if either the heart rate or the stroke volume goes up, according to this equation, our cardiac output is going to go up, which makes sense, right? If every time your heart squeezes, it squeezes out more blood, that's our stroke volume going up, then every minute, you're going to be getting more blood to your tissue. Same thing with the heart rate. If you are squeezing out a sort of baseline amount of blood, but all of a sudden you're beating way faster per minute, you're still going to get more blood to tissue. So that's what we are tracking today, this week. Okay. So we took a brief look back at our autonomic nervous system, and we were talking about this first part, talking about our nodes and their firing rates, and the fact that at rest, we're actually below our usual sort of resting heart rate for the SA node because our parasympathetic part of the nervous system, that rest and digest part, is in control. Okay, so we left off on this, where we were looking at sympathetic activity. So parasympathetics, rest and digest, keep your heart rate lower than that baseline for the sinoatrial node. So usually you're in this parasympathetic mode, but we can increase our heart rate, also our contractility, using our sympathetic nervous system, which sends out its hormones from the nerves and also from the adrenal gland, which is related to our sympathetic nervous system. Those bind to beta-1 receptors in our sinoatrial node, which increases the number of open sodium and calcium channels. Sodium and calcium channels both have those electrochemical driving forces pushing them into cells. So if we open a channel, they want to go in. They go in, their positive ions, means the membrane potential goes from negative to a little less negative, that's depolarization or excitation. And ultimately this increases heart rate because it makes it easier for us to fire off an action potential. So we end up doing it more quickly because we have less of a barrier to overcome. So we can also do this practice problem that I panicked about when I thought I would have to do math on the fly. So we will do it out slowly this time. Okay. I was panicking about the first part, getting a heart rate for no good reason, but hopefully some of you understand being afraid of math occasionally. Okay, so let's try this again. So we're just trying to find the cardiac output. We have a heartbeat every 0.6 seconds. We have our end diastolic volume, so the amount of blood left in the heart at the end of its relaxed phase, at the end of diastole. We have its ESV, it's end systolic volume. So that's after we've squeezed the blood out at 30 milliliters. We just want to know how much blood is getting out to the body every minute. So what our cardiac output is. Okay, so as we begin to set this up, we're reshaping this equation. So we're given our EDV and our ESV. What we want is our stroke volume from our practice problems last time. Hopefully we remember that we just subtract those two. The amount we're ejecting, that stroke volume, is just the difference between how much blood was left in the heart at the end of the relaxed phase versus how much blood was left in the end of the heart after we contracted, multiplied by our heart rate. Okay, oops, we can do that. Okay, so to get our heart rate, we're just dividing our minute by 0.6. So we get 100 beats per minute, filling in our EDV and our ESV. We're subtracting 160 minus 30 to get 130. Anyway, then we're multiplying out. So we get 13,000 milliliters divided by 1,000 to get 13 liters. Okay, so fundamentally what we've done here, I did tell you that we are mainly going to be focusing on, whoops, am I not sharing slides? All right. There we go. Now I'm sharing slides. So this is all we have done. So this will be there. Okay. Let's do it. Okay. Let's click. There we go. So when we look at this in the future, this stuff, does that kind of tell the math? I'm probably not going to make you do the math at the test. So like I said last time, what we're going to do is really just focus on the relationships between these things. So we're going to be focusing on, okay, what happens if the heart rate goes up? What happens if the stroke volume goes up? Or what if it goes down? Same thing with these properties. What happens if the end diastolic volume goes up? What happens if our end systolic volume goes down? You can do actual calculations in phys lab. They like math. So that's our cardiac output stuff. So this is showing us an increase in heart rate and what that would do for our cardiac output. So we ran through the sympathetic nerves, right? So we just saw how the sympathetic nerves would increase our heart rate, right? So this is increase in heart rate for right now. We just increased to that baseline for the sinoatrial node. So we can see that we have 13 liters of blood going out to tissue per minute. Whereas last time when we talked on Wednesday, we saw that it was like 5 or 6 or so liters at rest that you're pumping out to tissue. So this is a more typical number for if you're active, as you're getting into exercise. It can go higher than this. So you can increase the amount of blood traveling to tissue per minute a fair bit through increases in your sympathetic nervous system. Okay. So we're going to go through what that looks like from our cell perspective. So this is really just pretty much traveling through that flow chart of what's going on with our sympathetic nervous system and the heart, but we're looking a little more in detail. So what we're looking at here, right? So here we see our neurotransmitters associated with our sympathetic nervous system. Okay, so our neurotransmitter here is norepinephrine or epinephrine, either of them combined to this beta-1 adrenergic receptor. Okay, so here we see that hormone or that neurotransmitter coming out directly from our sympathetic nerve. Okay, so it's binding into this beta-1 adrenergic receptor. The beta-1 adrenergic receptor, all our beta adrenergic receptors are G protein coupled receptors. So we see this G protein splitting off and activating this other enzyme that creates cyclic A&P, which is our second messenger inside the cell. So that's what tells our cell to do stuff. Okay, so we can see this is an increase in the activity of this enzyme making cyclic A&P. Okay, so from this second messenger pathway, that's when we see the actual effects on ions. So from the second messenger pathway to the things we're doing are opening up some sodium channels. These sodium channels happen to be called funny channels. I don't really know what's funny about them, but yeah, it's what they are. Also calcium channels. So you don't need to know their exact names, just know that we're opening sodium and calcium channels, right? So we see these positive ions coming into the cell. So they were out here, now we're pulling them in. Okay, so they're going down their gradients along with the appropriate forces, depolarizing the cell. We have the reverse thing happen with our parasympathetic activity. Okay, so sympathetics and parasympathetics are like opposite sides of our dimmer switch. We're just going back and forth between them. Usually they're both innervating the same place, just have opposite effects. So since our sympathetic nervous system increase our heart rate, our parasympathetics are going to decrease our heart rate. Okay. So the parasympathetic activity here is coming from a parasympathetic nerve. In this case, it's a nerve we know. The vagus nerve is responsible for most of the parasympathetic innervation, say in your body. It goes all the way down to your intestines. So we've seen it coming off the brain, going all the way down to the intestines. So the vagus nerve is going to your heart, providing parasympathetic innervation there. Okay, so the vagus nerve carrying parasympathetics links up with our sinoatrial node as well. So it's going to the right atrium to that sinoatrial node. And our parasympathetic nerves, and they're not norepinephrine and epinephrine. They're giving off a different neurotransmitter. They're giving off acetylcholine. Okay? So acetylcholine was the neurotransmitter associated with our postganglionic parasympathetic neuron. Lots of words. But that means we're going to see a different receptor type. So instead of seeing those beta-1 adrenergic receptors, adrenergic like adrenaline, which is another word for epinephrine, we're now going to have cholinergic receptors because we're talking about acetylcholine. Okay, they happen to be muscarinic cholinergic receptors. Those are the ones that take like a little bit longer to work versus our nicotinic cholinergic receptors that we saw in the synapse between our preganglionic and our postganglionic nerves. And I'm telling you those things about the nicotinic, not because they're going to be on this exam, but because we also have our final coming up. So we might as well start studying. Okay, so muscarinic cholinergic receptors are also found in the sinoatrial node. Okay, so we're still going to ultimately open some channels. We're going to open now, though, our potassium channels. Okay, so potassium is a positive ion. It's still a cation, but it has different gradients. It has different forces on it. So potassium doesn't want to go into cells. It wants to leave cells. So when we open those potassium channels, potassium leaves our cell, okay? So this is moving us farther away from a threshold. This is making it harder to depolarize, harder to set off an action potential, because our action potential is that wave of positive charge inside our cell. So at the same time, we're opening those potassium channels. We're doing another thing that also makes it harder to depolarize this cell, which is that we're closing calcium channels. Right? So calcium was important for action potentials in the heart. Okay, so closing these calcium channels really makes it hard to send off an action potential as well. So these two effects together decrease our rate of depolarization. Right, so we're decreasing depolarization, and fundamentally an action potential is just a big wave of depolarization. And in fact, we are actually hyperpolarizing the cell. So hyperpolarizing, when we talk about the polarity of a cell, kind of talking about the fact that it has that negative membrane potential. So when we hyperpolarize it, we make it even more negative. So that is related to why we have less depolarization. Right? We made ourselves even more negative. It's hard to reach our threshold. So the overall effect is that we decrease the heart rate because we're slowing down these action potentials because we're just making it hard to depolarize this cell. So that's the effect of our parasympathetic activity on our sinoatrial node. We can look at a picture of that too. Okay. So reviewing what those receptors look like. So we have acetylcholine. So acetylcholine coming from our postganglionic parasympathetic nerve. Okay. So ultimately coming from our vagus nerve. Linking up with a muscarinic cholinergic receptor, cholinergic choline. Okay. So the muscarinic cholinergic receptors are also G protein coupled receptors. Okay, that's why they're slower than the nicotinic ones, which are not. Okay, so we can see the two actions that follow from activation of this G protein. So one over here is that we are closing our calcium channels. Right, so we'll note this negative, right? And we see it bouncing off, it's closing. And on the other side, we see that the G protein is increasing the open state of these potassium channels, right? So here we see our potassium channels open. So our potassium is leaving the cell because that's what potassium wants to do. So we have both these effects. And if we didn't know that this was parasympathetic, if we didn't have that word there, or we didn't see acetylcholine, we could still identify this receptor, right? Because we don't see that second messenger in here. We don't see cyclic A&P. So we were able to tell we had even beta adrenergic receptors specifically when we saw that activation of cyclic A&P. So we could also graph the overall effects that we see here, okay? So what we're tracing, we're looking the amount of time on our x-axis, and we're looking at the membrane potential on our y-axis. So essentially, we're looking at action potentials, which are really just a peak, right, of membrane potential. So that peak depolarization, really our action potential. Okay. So we're first looking at the one at rest. So I'm gonna make this thicker, that'd be great. Okay, so for our first sort of at rest, you're just sitting around, I don't know, watching TV, something like that. Your heart is depolarizing, right? You have a heartbeat, good for us. So here we got one heartbeat around 0.4 seconds. And then we have another one around 1.2 seconds. And that's the baseline that we're starting from. Okay, so we have 0.8 seconds here between our heartbeats. So, and each heartbeat, right, is telling us that we have like one round of our cardiac cycle. So we can then look at what the sympathetic versus the parasympathetic nervous system is doing to this heartbeat, right? So we are going to first speed up with the sympathetic nervous system. Let's do that now. Okay. All right. So with our sympathetic nervous system, that's our line in green, but I'm still going to trace it in red for us. Okay. So what we've done by binding to those beta-1 adrenergic receptors in the sinoatrial node, we've made it easier to depolarize these cells. We made it easier to depolarize, so it's going to happen quicker. So fundamentally, that's why our heartbeat gets quicker. So now we see that we're reaching that threshold a little sooner than we did with our resting state, right? We've made it easy to depolarize, so it's really easier to depolarize. We get there quicker, okay? Which means we also fire off our action potential a little sooner, okay? We go back to rest, right? Nothing changes really about that, except maybe we don't go down as deep as we might in some other situations. We still have this depolarization effect. Our sympathetic nervous system is still active, okay? So it happens again. And again, this is just happening a little faster than it would otherwise because we've made it a little easier to depolarize this cell. Okay, so on this graph, we now see 3 peak depolarizations, right? 3 action potentials, which are going to correspond to 3 heartbeats in this time. So we see that our time between heartbeats is a little less, right? So that's our sped up heartbeat. And that's how it links up with this membrane potential and this depolarization. Now, the exact opposite is happening with our parasympathetic nervous system. So that rest and digest part of the autonomic nervous system. So that's the one in blue, right? So on this graph overall, we just see the 1 action potential. You can see that here we've started way down low. So that's the hyperpolarization piece. Right, so the hyperpolarization means we're starting at a resting point even lower than normal, right? So significantly lower, we can see here, okay? Which means it takes us a long time to get up to threshold, right? So we can see that we're slowly going up, but it's hard because we have these closed calcium channels and we started out with a lower membrane potential to begin with. It's just hard to get to threshold. So it's just harder to create this action potential, so we do it less frequently. So here we have a much lower heart rate because of this difficulty getting to the action potential. Now, low heart rate isn't bad, right? Like it's adaptive in certain situations. You don't want your heart beating super fast, super hard all the time while you're asleep. Wouldn't be good, right? So when I say it's harder to do this, that's not necessarily a problem, right? But it does slow down our heart rate. So we also have some hormonal effects on the heart rate. We're going to go through this in a little less detail. So you just kind of want to associate them with a sped up heart rate or a decreased heart rate, essentially. So when we're thinking about our hormones, one of our really important hormones is epinephrine. So we remember that epinephrine is associated with the sympathetic nervous system. It's coming from our adrenal glands. So it's going to overall have the same effect as the sympathetic nervous system because it can even bind into some of those same receptors. Okay? So epinephrine works just like that sympathetic nervous system pathway did. So it's going to increase our action potential, increase the rate of sinoatrial node firing down that conduction system, which means that we are going to be increasing the number of those action potentials per minute. It actually also increases how fast they can pass down a muscle fiber. So that depolarization effect is a little more widespread even than we looked through on that little receptor down there. Okay, so epinephrine controls heart rate in the same way that the sympathetic nervous system does. Glucagon, we're not going through any specifics here, but it also increases heart rate. Okay, so increasing heart rate here. Now we are going to think about integrating these things together. So when we integrate our heart rate control, we're going to have this dual innervation, right? So it's not a light switch, yes sympathetic, yes parasympathetic. We're somewhere in the middle. We have both of them going to the SA node. So when we raise activity in our sympathetic nervous system, so increase how much those sympathetic neurons are firing, they go to the sinoatrial node, raising the heart rate, but there is still parasympathetic innervation there. So this is all about which one is dominant, not totally off or totally on. Something we want to remember about our autonomic system. Okay. But if our parasympathetic nervous system is predominating, if it's in control, which it hopefully is for all of you right now, it's going to lower your heart rate. Check mine again. My sympathetic nervous system is in control of me right now, but hope that's not true for you. Okay. Parasympathetics relax you, lower your heart rate. Okay. If you have a bunch of epinephrine circulating, so epinephrine synonymous with adrenaline, that's associated with the sympathetic nervous system, works in a similar way. So that's also raising your heart rate. So all of these things would kind of be happening at the same time. Because you have sympathetic nerves firing to your heart, you have parasympathetic nerves firing to your heart, you have some amount of epinephrine in your body. So it's all about the varying levels. So if we're talking about something, we're going to describe it as the sympathetic nervous system dominating, or we're going to describe it as increased levels of epinephrine or high levels of epinephrine, rather than just like there is a sympathetic nervous system. So here's that equation again. All right, so we've been tracking the changes in heart rate here. So all of those pathways that we were talking about, so the sympathetics, the parasympathetic, and that epinephrine and glucagon, they were all acting on heart rate here. All right, so they were increasing our heart rate if we're thinking sympathetics or epinephrine or even that glucagon, okay? Or they were decreasing, really, if we're thinking about our parasympathetics. Okay. Cool. So their effect on cardiac output, we're thinking about these ones, it's going to be an increase. Right, so we're going to increase the blood flow to tissue if we increase the amount of firing through our sympathetic nervous system, if we increase our circulating amounts of epinephrine, or even if we increase glucagon levels, versus if we increase our parasympathetic firing, we're going to decrease the heart rate, which means we would decrease our cardiac output. So that's the kind of thing we want to be able to do, want to be able to think about as we think about our cardiac output and the function of our heart. So honestly, I recommend when you sit down here at your exam, like probably not going to test you on this exact equation. We'll think about exactly what's going to be on there in the review, but I do recommend writing this down anyway, just so you remember it, so that when we start talking about, okay, this is going up, this is going down, you have your little note to yourself. At least that's how I would do it. Cool. So now we're going to talk about stroke volume, which is a little bit different. So we're going to have slightly different effects here. So we are no longer, when we're thinking about stroke volume, thinking about that conduction system, that electrical pathway from our sinoatrial node to our atrioventricular node, to those right and left bundle branches to the Purkinje fibers. Now we're thinking about things like ventricular contractility. So we're thinking about like how hard the heart muscle is squeezing out. So this is no longer about speed, this is about amount, okay? So the main factors that we're going to be thinking about here when we're thinking about stroke volume is we're going to be thinking about how hard those ventricles are contracting, ventricular contractility. And this is the biggest thing that we want to focus on, the contractility of the ventricles. These other two factors are kind of related to this. So it's actually true that the amount of blood in the heart is going to have an effect on how much those ventricles can contract, how much blood they can push out, because the movement of that blood was all about pressures, right? So as we change the amount of blood in the heart, some of these pressures are going to change. Okay, so we'll be looking at the end diastolic volume in particular, also something called afterload we'll touch on briefly. So when we're talking about the contractility, right? You think about a muscle, Contractility, contracting, squeezing, right? So we're talking about how hard the heart is squeezing. If we squeeze harder, we squeeze out more blood. Hopefully pretty straightforward. That's not a trick. But the thing we want to remember here, that when we looked at that diagram of what nerves are going to the heart, right? Both our parasympathetics and sympathetics were going to our conduction system, especially to that sinoatrial node. But our parasympathetic nerves were not going to the ventricles, or at least they're not providing substantial innervation there. Really just our sympathetic nervous system that gets to that myocardium of the ventricles. So when we think about stroke volume, we're really going to be thinking about the sympathetic nervous system specifically. So both the parasympathetics and sympathetics affect the heart rate, right? To affect how fast your heart is beating, speed it up or slow it down. But it's really just the sympathetics that say, okay, are you squeezing harder? The parasympathetics don't really have an effect here. Okay? So this is one almost exception to that dual innervation. We don't consider it a full exception because the parasympathetics are going to the heart as an organ system overall. But we want to make sure we know that it's really just the sympathetics here that are affecting the ventricular contractility and therefore stroke volume. So the sympathetic nerves here are going to innervate the muscle cells, which we call the myocardium, right? So the actual contractile part of the heart. So cardiac muscle was one of our 3 types of muscle. We talked in depth about skeletal muscle. We basically mentioned that smooth muscle exists, and you know that it's going to come back a bit when we start to talk about blood vessels next year. Okay? And cardiac muscle is our 3rd type, which is what we're talking about now. Okay, so sympathetic nerves are innervating these muscle cells. They're going to give off some norepinephrine, right? Just like they did when we were thinking about that sinoatrial node. And just like with the sinoatrial node, these muscle cells are going to have beta-1 adrenergic receptors. And those beta-1 adrenergic receptors, when they bind norepinephrine, are going to upregulate, so increase that cyclic A&P second messenger system. So we're still going to be making more cyclic A&P. Okay. So overall, this effect, this pathway is very similar, pretty much the same as the effect of the sympathetic nervous system on the sinoatrial node. It's just now we're going to be affecting a different property. Instead of affecting the speed of action potentials, we're affecting the force of contraction. Okay, so the way we do that is we are now going to open more calcium channels. So the same. We know that calcium, from when we studied our cross-bridge cycling, right, back when we were looking at how muscles function and how they contract, we know that calcium is really important for that contraction, right? It's the presence of calcium that allows us to slide filaments past each other, because it's the calcium binding to the troponin, pushing aside the tropomyosin that exposes the binding sites so that actin and myosin can bind to each other. Okay, so our sympathetic nerves releasing norepinephrine, binding to beta-1 adrenergic receptors. Ultimately, our second messenger system opens up calcium channels. It also increases how much calcium we're releasing from the sarcoplasmic reticulum, which is that sort of modified endoplasmic reticulum in our muscle cells, where we're storing calcium for when we want to contract the muscle. Also happens to increase our myosin ATP rate a bit, so we're using energy faster. We're breaking that ATP molecule a little bit faster, which means we can go through more cross bridges, which means we can contract a bit more forcefully. Okay. And we're also enhancing the rate of reuptake of the calcium to the sarcoplasmic reticulum. So we're also helping sort of quickly turn this process off at the end. Okay. All right, so if we look at this, we see the same thing as we saw with our sympathetic nervous system and its effect on the sinoatrial node. We have our norepinephrine, or epinephrine would work here too, binding to our beta-1 receptor, turning on this cyclic A&P. Okay, so that's the same as before. The same as before, even, we open up a calcium channel. Okay, so that's the same as with our sinoatrial node as well. but we're in a muscle fiber. So we are also concerned now about our sarcoplasmic reticulum. When we see that sarco, that often tells us that we're thinking about sort of muscle cell. All right, so sarcoplasmic reticulum is releasing calcium also. Okay. So it's a second source for that calcium, increasing that cross-bridge cycle. So we can see here that the calcium has bound to the troponin, pushed aside that tropomyosin, and now we can see these exposed myosin binding sites on the actin. So the myosin can do its thing, starting that cross-bridge cycle, pulling those filaments towards the center, so making that muscle fiber shorter, essentially. And at the end, we also relax relatively quickly here because we want to get to our next heartbeat, right? So if it took us a long time to slow down to relax after contracting the heart, that would kind of mess with the whole, we've also sped up our heartbeats thing, right? So we want to squeeze forcefully and quickly, but we also got to relax because we have a fast heartbeat also coming from that sympathetic nervous system activity where it's touching the sinoatrial node. So if we compare our ventricular activity, so those ventricles, we'd be looking at time and we'd be looking at the force. Okay, so the force is our tension measured in grams. Okay, so at rest, you see we got some baseline tension, right? You do have a heartbeat, your ventricles are contracting, but with sympathetic increases in sympathetic activity, we also see an increase in tension, right? So we have a higher peak here when we have a lot of sympathetic activity. That's that fight or flight autonomic part of our nervous system, right? So we're going to squeeze those ventricles really hard. We squeeze them kind of quick, right? This peak is earlier in the time point, and we can see that we're back to rest a little more quickly as well. Right? So we have this sharper, higher peak with our sympathetic activity. So there's no significant innervation of these contractile cells from the parasympathetic. So this is just a reminder. And we're looking again just at this whole autonomic system. This is our overview. So our sympathetics coming from the thoracolumbar spinal nerves, going through our sympathetic chain, are going to our sinoatrial node up here at the top of our right atrium, also going to our atrioventricular node down here at the bottom of our right atrium, but they're also going to the myocardium itself, so actually to the muscle, versus our parasympathetic nervous system, specifically really the vagus nerve, is just going to those two pacemaker cells, those two nodes. For hormones, epinephrine still just works like the sympathetic nervous system does because they share those receptors essentially. Right? Those receptors are responsive to both norepinephrine and epinephrine, although they do sometimes have preferences for which they prefer. Okay? So that epinephrine is still binding to our beta-1 adrenergic receptors. Other hormones also increase the force of contraction. So essentially, we're really focused on increases here a lot with our stroke volume. So thyroid hormones, right? So coming from your thyroid gland, insulin, so that response to eating a meal, to eating something containing glucose, also going to increase the force of contraction. Even so is glucagon, right? So there are a lot of things that can increase our force of contraction here. Right. So now we're going to get to our end diastolic volume and its effect on stroke volume. So this is going to be like kind of our last major thing that we're going to touch on here. Okay, so our end diastolic volume, diastole, is when our heart, or specifically our ventricle, is at rest, right? So we're in the relaxed state. Now, that volume can be different, right? You can have more volume, you can have less volume, and that is going to have an effect on the container holding it. And by the container holding it, I mean your heart, right? The blood is in the heart is your container here. So if you have a higher end diastolic volume, means you have more blood coming into your heart, you have more stuff in the heart, and this can stretch those muscle fibers a little bit. So think about like filling up a water balloon, right? When you put more water in, those will all stretch, right? So that's kind of what we're talking about here with our end diastolic volume and those walls of the heart. Okay. So when we stretch those muscle fibers, here's where we want to come back to one of our topics that we did when we were talking about our skeletal muscle. Okay. So this also is true for cardiac muscle, that we have an optimal length. So we have an optimal length for our muscle fibers where they're going to squeeze harder. Right? We looked at our sarcomeres and like the amount of overlap between the actin and the myosin and how that can affect how well they can pull on each other. Right? So that's what I mean when I'm talking about the optimal length. We have the best amount of overlap, which means we can really latch on to those fibers, those actin with our myosin and pull them in. Okay. And your heart is not always at that optimal length. So you have to fill the heart to a certain amount to reach the optimal length. So your heart is actually hanging out at a little bit smaller than its most effective length. Okay. So if we increase the amount of blood in the heart, we stretch those muscle fibers a bit, and as we stretch them, they get closer to their optimal length. So when they get closer to their optimal length, that means the cross-bridge cycle just works a bit better, and we're going to create a greater strength of contraction. So because those muscle fibers are now going to be at their optimal, most effective length, we're squeezing harder, which means we are also increasing our stroke volume. Because our stroke volume is just how much blood we're squeezing out during that ventricular ejection phase, that third phase of our cardiac cycle. So what we're saying here, right, an increase in end diastolic volume would increase our stroke volume, which would increase our cardiac output. And the reason for that is because our muscle fibers will be closer to their optimal length. So we can squeeze harder. We have an increased strength of contraction. Now we can start to link that up very a little bit to our next topic that we'll start off in A&P2 and think about blood vessels. Okay. So when we were thinking about the heart, we've been drawing, hopefully we remember, 4 chambers, right? We have our right atrium, our right ventricle, our left atrium, our left ventricle. Mostly we've been drawing arteries to this point, right? So we know our right ventricle is going out to a lung. Got some lungs. Okay. Our left ventricle is just going out to your whole body through the aorta. I like to draw that arch of the aorta because it's pretty characteristic, but it's going to your whole little stick figure person. Okay. So fundamentally that's happening with our arteries, but we also have veins, right? The veins are how our blood is getting back to the heart. So specifically, our vena cava, we have a superior one and an inferior one. I don't care if you know the difference between the superior and the inferior vena cava at this point. We'll care when we get to lab, but not for now. Okay, so both of these are returning blood to the right atrium. Okay. So we're tracing through all of that, partially because we want to remember the pieces of the heart, but partially because if we increase the amount of blood coming to the heart, increases in venous return, this is going to increase how much blood is in the heart, right? So that venous return is happening during diastole, during that sort of relaxed phase when we're not squeezing, because that's when we have low pressure. So if we increase the amount of blood coming to the heart, we also end up increasing how much blood is in the heart at the end of diastole. So that's also going to increase your strength of contraction, which is also going to increase the stroke volume. So this whole slide is talking about increases in EDV that increase stroke volume and therefore increase cardiac output, just different sort of pieces that are linked together. So here we have just a picture that we don't need to go through in detail, but we're looking at those sarcomeres, those states right? So here we can see that stretch, right? So the stretched one is over here, right? So this is optimal on the right. Okay. And so we can see kind of why that is, right? You don't have much room to go here. We can't get much shorter. So we can't have a very forceful contraction because we're already kind of at this short length. Whereas here, we have a great amount of overlap. So we can see all those cross bridges on the myosin touching the actin, but we've got room to contract, right? We have a space that we can make shorter. So that's what creates that force of contraction. So this is a curve of the stroke volume. So how much we're squeezing out. And over here on the x-axis, we're looking at the effect of end diastolic volume. So that amount of blood in the heart, creating those different states for our sarcomeres, creating different amounts of contractility and therefore different amounts of stroke volume. Okay. So finally-ish, okay, we can talk about things called a family of curves. So one of the words on the previous slide, which, sorry, I didn't read aloud to you. What we were talking about is something called Starling's law, and we're specifying of the heart because we're going to have another Starling stuff in the spring. Okay, so this is called a family of Starling curves. Okay, and what we're looking at is a baseline curve, right? And then we're looking at how that curve shifts if you increase sympathetic activity versus if you decrease your sympathetic activity. So because we're talking about stroke volume, no parasympathetics here. It's just increase or decrease in sympathetics. And this whole curve is describing something about the heart. So we've kind of summarized in this picture two of our effects on stroke volume together. So what I mean is, what they've showed us is for a specific end diastolic volume, say, I don't know, 130 milliliters, right? Your baseline will have a certain number of milliliters of stroke volume. If you increase the sympathetic activity, you increase the contractility of the heart, so that goes up. But another way you can make that stroke volume go up, even without an increase in sympathetic activity here, say we're thinking about hormones now or something. Actually, no, let's not say we're working about hormones. Let's say we're just looking at the end diastolic volume. So if we're here at our baseline, and all we do is increase how much blood is coming back to the heart, we're still going to see a slight change in stroke volume. So each of these curves is the relationship between end diastolic volume and stroke volume. And then we draw a new curve above or below to show like the sympathetic nervous effect on that relationship between end diastolic volume and stroke volume. So we'll stop there. We do have just like one more slide here. So just associate the word preload with this end diastolic volume stuff. We'll mention this very shortly on Monday, but that's about it.